Hey guys, um, I decided that I would do the last couple of sections today, try to get them all posted today, which is Sunday, so that those of you guys that are wanting to just go ahead and get finished can get their homework assignments done, get them turned in, and wash their hands of this pandemic, so to speak. But those of you guys that don't, you'll still have the full amount of time to work on them, so these will be due on Friday, just like normal. Sorry, on Saturday, just like normal. And for those that are taking the AP exam, these are some extra little things that have appeared on AP exams inconsistently. And so sometimes they appear, sometimes they don't. And these are usually the ones I save for the end, anyways, because these are some really fun ones, or at least they're different. And this one today, like, is a completely different step in a direction for talking about calculus because it doesn't involve integration or derivatives. Whereas the next one, which would be 7.1 and 7.2, those are kind of where we start to see some more realistic applications of calculus, where you can start to see how it really becomes useful in terms of like industry. And so we've got a pretty short assignment tonight, page 421 slash 445, 33 to 55 odds. And we'll be doing a bunch of even examples in these sections. We're going to do 6 examples. So let's go ahead and get started. First of all, the big thing I want to point out about today is this exponential growth model, Theorem 6.1. So that's where I'm going to start my notes. This theorem comes from calculus, and how it fits in comes from calculus. But in general, you don't need calculus in order to understand it. We could actually teach this in like a college algebra class, or a class on, like, say, trig, and you don't need calculus to do it. But if you want to understand where it comes from, calculus is helpful. So the theorem states that you have a formula where it states that this function is a differentiable function meaning it, of course, has a derivative. In this case, y has to be bigger than 0. This is important for a lot of real-world applications because a lot of these theorems for exponential growth and decay deal with things like cellular growth, population growth, things that never really become negative because you can't have a negative population. And so y in this case has to be 0. The cool thing about it is that if you take the derivative of this function, it's just k times the original function, which means that the slope is just a proportional relationship to the original function, which is one of the properties of E. And so this is the only real calculus part, is talking about this topic right here. It's not even really used much in this section, but just where this piece comes from is calculus based. Now, in this case, this is referred to as the exponential growth model. In this case, there are a couple values to keep track of. C is the initial value. K is referred to as the proportionality constant. Although we usually call it like the growth rate or decay rate. Finally, the last little piece in here is actually this last little line. It's considered growth if k is greater than 0, so if k is positive. It's considered decay if k is less than 0. And we can see this by looking at a very simple example using something like Desmos. So here I have Desmos available, so you can see how these two equations look very similar. The first equation is the one done here in red. You can call this exponential growth because as time goes on, this function starts off very, very tiny, but definitely still positive, which is one of the requirements, right, is that y has to always be positive. And as we continue along this graph, it starts and then begins to shoot upwards very, very quickly gaining a number, in the hundreds in a very, very short period of time. And so this is referred to as exponential growth because this function is growing at a rapid rate while having these same properties. Whereas decay is the other end of the spectrum. It starts off very large here in blue, and then quickly descends to something very tiny over time. And so anytime we talk about exponential growth and decay, these are the two properties to keep in mind. Is something increasing over time or is it decreasing over time? And since we're talking about physical things, the physical nature of them means they're going to have positive values, and the rate at which they're changing is proportional to the original function that they're involved with. So this is Theorem 6.1. It's a statement about how to fit realistic problems with calculus. And in this case, exponential models are really big. If you want to talk about things like biology, things like physics, and a lot of your chemistry even, nuclear physics especially, a lot of these involve exponential models. Because if you want to talk about how, for example, an asymptote decays over time, it's an exponential decay for any asymptote. So if you want to talk about uranium decay, it's an exponential decay. Now it can be a slow exponential decay or a fast exponential decay depending on what value k is, because if we change k in these problems, we can change what this problem looks like. So if I change it from 5 to say 2, you can see how it shifts the function to be less steep. And if, as is the case with many of the ones we're going to talk about, if they're things like decimals, like say a 5% decay versus a negative 5% growth, you can see that, you know, these very much change how these models fit together. And they're still exponential in that they're still growing rapidly. I mean, still at 50, you're at 120. But, you know, as we go farther out to say 200, you're suddenly sitting there looking at something like 200 and in the thousands. And so this is still exponential growth. It's just, you know, how rapid or slowly this thing changes. And the blue line is still exponential decay because it's, again, how rapidly or slowly something changes in terms of the function. So again, some terminology here. The proportionality constant, it's the rate of change. So whether it's growing or decaying depends upon whether it's a positive or negative value. And for some functions, they may give you a proportionality constant, but tell you it's a decay. And so you have to then understand that if the word says decay, then it means the k is negative. If it says growth, then that means the k is going to be a positive number. And so these are big hints that in a lot of problems, sometimes they'll mention that, you know, you have an exponential decay of 5%. Well, that means it's going to be at 5%, which is 0.05, and it's going to be a negative 0.05. And so if I look at these two functions, how do we read them? Well, in red, we would say it has an initial value of 10, and that it is an exponential growth at 5/100ths, or 5%, for every unit of time. In this example, the one here in blue, we would say that this again starts at 10. So you can see I have my initial value of 10. But it is decaying at a rate of 5%. And so you can see that these two functions, while very similar, serve very different purposes. One is decaying over time, the blue line. One is growing over time, the red line. Well, that's all the major pieces we need in order to do today's problems, so let's actually look at some examples now. A lot of the other stuff that's talked about is just varying realistic situations, like exponential growth and things like fly population. Things like radioactive decay, which is the main one we're going to talk about, using half-life models. Declining sales, and so Newton's law of cooling. All these are exponential models. But the ones we're going to primarily focus on are going to be things like radioactive decay and interest. So, let's take a look. Starting with our first example, we're going to go through a few of these today using our Theorem 6.1 to do all of them. The trick with a lot of these is that there's a lot of extra calculator work, and some of them ask you to do things like graph them in order to see what they look like, so let's take a look. I'm going to start actually by doing our first problem together, number 33. The reason being is there's not one like it in your homework that is even, and so I think it'd be really helpful to do one like it here. So number 33. It says complete the table for the radioactive isotope. It says we have an isotope. This is radon 226. Ra stands for radon, and 226 stands for its atomic number, or in this case, the isotope number. It says it has half-life in years of 1599, and has an initial quantity of 20 grams. So the thing asks, what's the amount going to be after 1,000 years, and what's the amount after 10,000 years? The trick with the problems tonight is you're going to have to do a lot of substitution and solve. Because for a lot of the problems, you're going to be dealing with incomplete information, as is common in many realistic scenarios. And the second thing is using the information they give. So let's take a list here about what has been given to us. We've been told in this problem that we have this random radioisotope. In fact, it doesn't matter what it is. The fact that it's 226 radon has no bearing whatsoever in this problem, except the fact that this is meant to be realistic. They've told us it has a half-life of 1,599 years. They told us we have an initial quantity of 20 grams, and it wants to know what's the amount after 1,000 years and the amount after 10,000 years. So let's talk about what some of this information means, because some of these details are really important. What's the term half-life mean? The term half-life means that if I have an initial quantity, let's call it, C, that means that after, this many years, the amount we have left is going to be C over 2. And so in this particular example, what this means is that if I start at 20 grams, then after 1,599 years, there will only be 10 grams. That's what the term half-life means, is that this statement is true. Now what's important about this statement is it's actually given us two pieces of information. One piece that it's given us is we have an initial value, which means that at time 0, our output should be 20, because that's what initial condition means. So our initial value is at time 0, it should be 20. But it also means that after time 1599, it should be 10. This information is going to allow us to find some missing variables, because this first one is actually not very helpful at all. It doesn't actually tell us very much, but the second one tells us a lot. So let's go to our formula. Our formula states, and I'm going to use the entire page for this because this problem, it can be done quickly, but I want to showcase all my steps. Y equals C e to the k t. First of all, let's note a couple things here. Number one, I know because this is decaying over time that my k is going to be negative. Because again, decay is always means it's less than 0. Second thing, I know that in this example, my initial value is actually 20, which means I already know part of the formula. Y equals 20 e to the negative k t. Well, guess what? I can now use these two pieces of information to figure out the one thing we don't know, which in this case, we need to find out what k is. K is usually the thing we're looking for. With the other option being C. And so the big trick about using these problems and this information is, how do we figure out what the half-life is supposed to be? Well, that's going to be a proportionality constant. So let's do this. If I use this first point and plug in 0 and 20, I can't find k, because 0 times k is going to mean I end up with 0 up here, which isn't going to do anything. And so it's better to plug in this case, my second point. So that's exactly what I'm going to do. My y value should be 10. Negative k. And in this case, my t is supposed to be my half-life here, which is 1599. So notice how I use the given information that I have a half-life at 1599, meaning that I will start at 20 and get halfway through that 20, so from 20 to 10, in 1599 years. And I use that to plug into my formula, which now gives me a formula that has just k in it. Now this becomes an algebra problem. So I can take my algebraic steps, divide by 20, so I get 0.5 equals e to the negative 1599k. And now I can use some properties of algebra to solve this we talked about in the last chapter, where I use a property of natural logs. So I can use ln to get this to become an individual number. So I get ln of 0.5 equals, remember the ln and the e are supposed to cancel, leaving with negative 1599k. I can then use a calculator to calculate what ln of 0.5 is, and then divide to figure out what k is. Remember, the natural logarithm is just a number. So now I'm going to use my natural calculator ln of 0.5, and I end up with negative 0.6931. Okay, negative 1599. Okay, I can then divide to get k by itself. So I divide should be negative 159. And so I end up with this answer, 0.0004334. Okay. And so this means that I have a new formula for this problem. My formula for this problem is y equals 20 e to the negative 0.0004334 t. So this is my formula. Why is that so important? Because if I know the initial value is 20 grams, I can use this information now to figure out how much is left after 10 years and how much is left after 10,000 years. So I'm going to do that. At this point, I'm going to actually go to a better calculator here. I'm going to use my beautiful, wonderful TI-84 calculator. Open Sesame. Okay. So now what I'm going to do is I'm just going to type in 20 e to the negative 0.0004334 times 1,000 and get an answer. And I can do the same thing up here, but 20 e to the negative 0.0004334 times 10,000. And see how much material I have left. So I do 20 e. My e button on here is right there. E to the negative 0.0004334 times 1,000. That tells me, remember my initial value when I started was 20 grams. Well, after 1,000 years, I will have 12.966 grams. After 10,000 years, I will have 0.262. Was there 6223 grams? So with this section and its homework, a lot of the big pieces are understanding how to take given information. Oh, let me get this out of the way for you. How to take given information, like you have a half-life with initial value, and use that in turn to develop a formula, and use that formula to develop solutions. And so after 1,000 years, this 20 grams will reduce to 12.966 grams. After 10,000 years, that 20 grams will reduce to 0.2623 grams. Just to let you know, the amount that is lethal for 226 radon, the amount that's lethal to humans is like 1/1,000,000 of a gram. And so after 10,000 years, this is still going to kill you. Just fun facts. Fun. So this is the primary thing that's going to be based upon tonight's homework assignment, is the ability to use given information to develop a formula, most of which is going to be algebra, and using some of the properties we talked about in the previous chapter. And you'll notice that there's zero calculus in here, which is nice for some of you that have not liked some of the calculus at the end of the year, because it can be a little rough. It's got a lot of components to it. There's no power rules or quotient rules. There's no integrals to do. This is it. It's just using the information in a different way. And the formulas are developed using calculus. That's it. So let's look at a few more examples, and we'll call it a day. Let's look at 34 now. So on number 34, we have same function, 226 radon, 1599. In theory, this should have the exact same E value and K value, but unfortunately, like, it's not one of those things that we can easily fill in. So let's make sure. So let's do it. We know we have I think, well, that's nice. For number 34, we should be able to use the exact same E value. Yeah, because they skipped the initial quantity. Perfect. Okay, so I'm going to use the information I gained from the previous one to fill out a new table. This is helpful since you're supposed to be doing 35. We've already done 33, so you can use the information to fill out 35 as well. I'm going to make my little table. And so we want to find the initial quantity. We want to find the amount after 1,000 years. And the amount after 10,000, when we know that after 1,000 years it has 1.5 grams. Okay, so the formula we had before was y equals 20 e to the negative 0.00043334 t. Now, here's the thing. This 20 is no longer valid because this is my initial value. Well, I don't know what the initial value is. It's going to have a different initial value. I do know this value, which, if you know your mathematics, what this means is that when t is 1,000, my output is 1.5, meaning I actually have a point. So if I don't know my value c, y equals c e to the negative 0.00043334 t, I may not know my value c, but I do know a point, which means I could plug that point in and be able to get to a solution. I have 1.5 equals c e to the negative 0.00043334. My t in this case is 1,000. And I can use this to figure out what my initial value is. Just like before, this is going to be an algebraic problem. Being able to solve it algebraically is going to be the big detail. In this case, it's important to note that this is a number. There's no variables in it, so it's just e, which is a number, to a power, which is a number. And so if I want to figure out what c is, what I could do is just take 1.5 and divide it by this number, e to the negative 0.00043334 times 1,000. And this would tell me exactly what my initial value was for this problem, which is exactly what I'm going to do. So I will now pull up my calculator again. Boop. I'm going to take 1.5 and divide it by e to the negative 0.00043334 times 1,000. That's 1,000, right? Yep, here we go. This tells me that my initial value, my C value in this case, 2.3137 grams. How do we know it's grams? Well, I started with grams. Oops, let me get the calculator out of the way so you can see it. This tells me my C, which means I have a new formula in this problem. And that formula is this formula, but with the correct C. So y equals 2.3137 e to the negative 0.00043334 t. Now let's fill in some gaps here. My initial value, 2.3137 grams. Okay, I had to find that, and we did it algebraically. My amount after 10,000 years, I can go back to my calculator, use my new formula, and do 2.3137 times e to the negative 0.00043334 times 10,000 this time. 1, 2, 3, 4, 5. Boom. So after 10,000 years, I should have 0.0303 grams. Notice how we just used the given information in the problem to determine what the initial value was, filling in gaps in our formula. And then with those gaps filled in, we can get a new formula, which we can then use to actually evaluate the values we want to know. This is how a lot of science is done when we only know something specific. With this information, you'll notice that we can use to predict how much of something existed long ago or long into the future. So when they make claims about how, this much of the atmosphere used to be X material, like, you can do that because you're assuming exponential growth and decay. So in this case, this could be the present. We can think about it that way anyways. So maybe there's 1.5 now. So that means 1,000 years ago there would have been 2.3137. And then 10,000 years in the future, that might be 0.0303. And so you can use this information to say, okay, if I know at least one other data point, I can find other information. You can even use this backwards to figure out what, for example, the half-life is. And that is what one of our other problems is going to be when it comes to ones like 41. And so you can use it to predict things like percentages and amounts, which is pretty neat. Let's move on to 44. Same basic concept as 34 and 33. They've given me a table. You want to complete the table, assuming it's compounded continuously. At the end of the previous chapter, I pointed to a particular table which indicated that this same formula, y equals c e to the kt, is used for continuous growth or continuous compounded interest. And so in this example, let's see, in 44, it tells us we have $18,000. Nice little chunk of money, is my initial investment. Okay, and it's accruing at an annual percentage rate of 5.5%. Now, in terms of realism, that is very high for many accounts these days. Most common accounts are looking at like 2%, or even like in the single digits. It's like a 0.5%. Especially if it's a low risk account. The lower the risk, the lower this number is typically going to be. And so this is paying out really good. This is somebody's got a really good account set up here. How long will it take for the investment to double? And so this is another way that they can give you some information that is not necessarily what you're expecting. So the statement it says is, ask the question, when will this information double? What that means is, when will my 18,000 become 36,000? Like, how much time is this going to take? That's what it means when it says how much is it going to take to double. And so this is a very different question than like the previous ones, but it can be solved in much the same way. We're going to use this formula to figure out the two components we need, the C and the K, and then with those two pieces, we're going to figure out how long it actually takes to double this account and use that information to get to our answer. So let's do that. So, use information, I can now start to plug into my formula. So my formula is y equals, C is supposed to be the initial value. The initial value, it says, is 18,000. E, K. Now, a few things to note here. K is the interest rate, but this is a percentage. So I have to make sure to write that percentage as a decimal. Because I cannot have a percentage in my formula. I have to have a decimal in my formula. And then T is how much time is going to pass. Now, is this a positive or a negative? Well, this is an investment, which means it's going to be growing over time, which means this should be a positive number. So keep that in mind. Remember, growth is going to be a positive K, decay is going to be a negative K. You have to indicate which one in order to go forward. So this is the formula you're supposed to use. And the question asks specifically, when will this thing double? Meaning, when will I go from 18,000 to 36,000? Well, this is a Y value. It's an output. Meaning I could do a substitution 36,000 equals 18,000 E. But I don't know how much time this is going to take. So I end up with a formula with only one variable, t, which is convenient because I can solve this. I divide both sides by 18,000. You notice that when you do, you end up with 2. Because what have I done? I've doubled my investment. 0.055 t. And then just like before, if I want to get rid of an e, I can use a natural log. Remember, natural logs and e's are meant to be canceling relationships. So I end up with the natural log of 2 equals 0.055 t. And then I can divide by both sides by 0.055 and get to an answer. So my t in this case should be ln of 2 divided by 0.055, which in this case, using my calculator, I can determine that number to be, calculator, ln of 2 divided by 0.055. It's going to take 12.6 years. How many decimals do you go to? If it doesn't say, go until you're comfortable. I usually think at least 3 digits is good. The farther you go, like the better it's going to be, but really it's how much you want to explain this. If I'm talking to a scientific person, going to 8 digits makes sense because the first 3 are zeros, and so the next 4 are really the ones I really care about, and so this actually makes sense to use this number in this context. If I'm talking to my best friend trying to tell him how to invest, I'm not going to say 12.602676601. Like, that's just a waste of my time and their time. I'm just going to say 12.6 years, or a little over 12 and a half years. And so this is how long it's going to take for this investment to double. And so at 5.5% interest, it's going to take 12.6 years. Now then the second piece of this question, the arguably better piece, is asking how much it's going to be after 10 years. So what I can do is I can take this exact same formula that I now know works and do y equals 18,000 e to the 0.055, and my t in this case is going to be 10 years. So I would then just do my algebra, which would be 18,000 e 10 times that would be 0.55. And so now I can use a calculator to get that answer as well. So tonight's problem is going to be a lot of calculator pieces to them, so make sure you got your calculator ready. 18,000 divided, not divided by, multiplied by e to the 0.55. So how much is it going to be after 10 years? After 10 years, so the y value after 10 years is going to be 31,198.55. I go to 2 decimal places because we're talking about dollars, so it makes sense to go to 2 decimal places. And so this is exponential growth, and it's just how you kind of figure the pieces out. Notice that in this case, the information they gave me was that it doubled. And so I have to interpret the word double into algebra, into mathematics. What does doubling actually mean? Well, it means taking the initial value and making it twice as much. So 18,000 becomes 36,000. And so I can use that to figure out how much time that's going to take, and then use that to figure out t using algebra. And the other one's just a simple plug and chug. Notice that for the other ones like 45 and 47, they've told me, instead of telling me their rate, they've told me, an amount after a certain amount of time. And so we can work backwards, just like we did on 34 and like we did on 33, in order to figure out what the missing piece is using algebra. I want to do at least one more problem, so let's go ahead and take a look. And in this case, I want to look at number 54. So 54. The big part about 54 is that they have not just mentioned compounded annually, monthly, daily, and continuous. So part D is like we've already done. However, parts A through C is stuff from 5.7. So just a second, I'm going to go back and grab that formula because we're going to need it for this section. Apologies, it was not 5.7, it was back here in section 5.5. In this case, these are the two formulas you're going to need for this section. Notice that compound is continuous. That's part D, is this bottom formula, which is P e to the RT, which you'll notice is suspiciously similar to C e to the KT. That's because of the same formula. It's just they use principal instead of initial value, which is the same thing. R is rate, whereas it's proportionality constant, which is the same thing. And then T is time, so T is time. And so the big difference on this one is that for parts A and C, or parts A through C, we're going to be using the formula A equals P1 plus R over N to the NT. And so I'll do parts A, B, and C with you guys here. Let me get back to that page. Okay, here's that page. So let's talk about part A. It says you have a 7% interest, and it says we want it to double, and it says annually, monthly, daily. Okay, so let's talk about part A. We have in this problem for number 54, and like you have 53 and 55, 54, we have a rate of 6%. We have an initial value or principal of $1,000, and what we want, so this is our want, call it Q, is we want it to double, meaning I want it to become $2,000. So watch how this formula can generate that result. Well, we know a couple of these, so we can fill in the formula. We know what we want is our $2,000. We know that we started with $1,000. We know the rate for number A is 6%, which we need to put as a decimal, 0.06. Now the question is, what's N and what's T? Well, T is unknown, so we're going to leave T as T. Now it says annually. Now in this formula, it's based upon how many times it's done. So if this is annually, that means we're going to have just one. Yeah, as you can see right here from our formula, it says this is the number of compounds per year. So if it's doing it annually, that means it's going to be once per year. And so in this case, my N should be 1. Okay, going back to our problem. So this means we get this formula where we have everything except for T. Well, now I can use algebra to solve for T. Before I do that, I want to go ahead and set up part B just to kind of showcase the differences. For part B, it's very, very similar. $2,000 what we want. We start with $1,000. And then what do we get out of it? Well, we have 1 plus 0.06 out of. The difference between part A and part B is, part B it says monthly. Well, that means it's going to happen 12 times per year because it's every month. And so notice how this gets slightly different formulas for part B versus part A. For part C, it says daily. This means for part C, it's going to be 2,000 equals 1,000. 1 plus 0.06365. And we're assuming 365 just because, well, leap years don't exist in math sometimes. Okay, so this gives us the setup for A, B, and C. For part D, the math is actually a lot easier to do because for part D, we just do 2,000 equals 1,000 e to the r, which is 0.06 t, and then we can solve for t directly. And so for each one of these, all we have to do is, divide by 1,000, and then use the natural log, or in these cases, you won't use the natural log, you use this log, this base, in order to figure out what this is. So I'm going to do A real quick, just to showcase it. And then B and C should follow pretty easily, and D is like ones we've already done, so we should have it. So let's go ahead and look at part A. So I divide both sides by 1,000. So I end up with 2 equals 1 plus 0.06 over 1 to the 1 times t. Before I go any farther, I'm going to simplify some things. So 2 equals, so 1 plus 1.06 over 1. 1.06 over 1 is just 0.06. 1 plus that, so that should be 1.06. You don't have to do this math, but I'm choosing to. 1 times t should just be t. And now I can use a log base 1.06 on both sides to cancel and allow me to get log base 1.06 of 2 equals t. And that's part A. This should be my answer. And so I pull out my calculator. And for my, remember, to find the logarithms, you have to go to the math one, and then it's the second from the bottom. So we do 1.06 of 2. It tells me that if I did it, compounding annually, it would take me, it will double after 11.8957 years. Which is, that's pretty neat. By comparison, if we did the Part B version, give me one moment. If we did it with Part B's way, it would take, just a little bit less, 11.58, which is still, not too bad. Both these are pretty reasonable. Compare this to Part C. In Part C, we can answer closer to 11.55. So again, each time it just goes down just a little bit. And finally, if we compound this continuously, just a smidge less. So, compounded over the course of daily, 11.55, continuously 11.552. So, 1,000th difference between the two, which isn't a lot, but, the bigger your numbers get, the more these things matter. And so it's important to note these kind of pieces and how they fit together and how they should work. So, from 54, a lot of these answers are going to be very close together. So make sure you go out far enough that you can indicate clearly which one's bigger and which one's smaller. So we had 11.8957. This is 11.58. This was 11.553. This is 11.552. And so they're all very close, 11 point something, but they are different. So there you go. This is all the problems we have in this section. I hope this was helpful. I hope you guys enjoy this. And we got 2 sections left. I'll try to get those posted today as well. Thanks. Bye. Oh, wait. 421/445, 33 through 55 odds.